All right, thank you everyone for coming. My name is Alan Gates. I'm one of the founders of Hortonworks. I'm also a member of the Apache Hive PMC and a number of other Apache projects. And I'm going to talk today about some of the work going on in Hive 2.0. So let me start by just some acknowledgements. The Apache Hive community has built a lot of awesome and interesting stuff that I'll be talking about, but just want to stress this is community effort coming together to build all this. Also want to say thanks. I stole some of these slides from some of my coworkers, and Sergey and Sid, so thank you to them for that. And then finally, I'll mention a number of Apache projects as part of this talk, and I often forget to say Apache in front of the project, so this is my disclaimer up front that these are all Apache projects, and Hive interoperates with a lot of these. Okay, so what I want to cover in this talk is a little bit of the history of Hive 2.0 and kind of just an overview of what's in there. I won't have a chance to go into the details or even to touch everything that's added, because there's been lots of work, as I'll show you, but I want to give you a little flavor of where the Hive community is going and the types of features that are being added. So one of the downsides of listening to old people talk is they always want to tell you stories about the past, right? Back when I was a kid. So in the Hadoop world, I'm an old guy. I've been involved with around Hadoop projects for 9 years now, so not quite since day one, but for a long time, so I can claim to be an old guy, so I'll tell you a little bit of history first. So as you probably know, Hive started out as a batch engine. It was translating SQL into MapReduce. That's what it was used for, partly because MapReduce was what there was. Everything on Hadoop ran in MapReduce, because guess what? There were no other options. So when all you have is a hammer, that's what you use. And that was great, worked well. About 4 years ago, people started to say, I have all my data, or much of my data, in Hadoop, and rather than just doing batch kinds of things with this, I'd like to do analytics, I'd like to do BI, I'd like to do more real-time kinds of things. And so Hive, along with a number of other projects, SQL projects, started to evolve into becoming much more of a traditional data warehousing solution on top of Hadoop, being able to do all those things that people have done for years and years with their data warehouses. In particular, the release of Hadoop 2.0 with Yarn, which enabled alternate engines other than MapReduce. Suddenly we were free to do many new and interesting things that couldn't have been done before. So over the last 4 years, Hive has gone through a pretty huge transformation from just kind of a batch ETL engine to, in addition to doing ETL, which it still does quite well, more traditional data warehousing workloads. So this is good in many ways, but it also caused a little bit of stress in the Hive community, because there were a whole set of users who were very happy with what Hive was, right? They didn't care about adding data warehousing capabilities. They didn't care about analytics, BI, reporting, whatever have you. They liked it as it was, and so for them, this came down to, you're changing a tool that I like. And try as we might, no matter how much we test, all those things, as you add new functionality to a tool, you often break, or at least temporarily break, existing things. So that causes stress for the people who are happy with the way things are, right? So how do we deal with this in the community? What we came up with was a compromise of, we don't want to stop developing Hive. There's lots of people who are Hive users who are very excited about the new stuff that's happening. So we'll compromise here, and we'll create a 1.0 branch that we promise is stable, it's backwards compatible, we'll continue to put bug fixes in there. Developers are free to put new features in there if they want. We're not saying you can't keep adding features to the 1.0 line, but you can't break things. You can't put in features that aren't backward compatible, that sort of stuff. And stability is more the stress here. And we'll create this new 2.x line where we put in, this is where a lot of the new work goes, right? And in the 2.0 line, we'll be backwards compatible wherever we can. We're not going to break things just for the sake of breaking things, or just because we think, oh, it'll be just a little bit better if I fix it like this. But there are a few things that you just kind of can't help or that really needed broken. And so we don't 100% guarantee backward compatibility. And I'll cover some of those areas where the backward compatibility issues come up. So Hive, the first release of Hive 2.0 came out in February. We just did a 2.1 release last week. And I just want to be clear, we don't consider this production ready yet. We would not yet encourage you to put this in your production pipelines, because there's, as you'll see here in a bit, there's a lot of new code in this, and it needs some time to bake out and get hardened and all that kind of stuff. So we're getting there, we're banging on it, but it's not there yet. So getting a little bit of an idea of how big these changes are. Over 1,000 JIRAs were resolved in Hive 2.0, as opposed to the previous point where it branched off of branch 1. Another 625 were resolved in 2.1. The vast majority of those 2.1 changes are bug fixes. As you can see, there's quite a few actually improvements and new features in the 2.0 line. So here I lay out some of the things I want to touch on. And again, there's lots and lots of stuff, 140 new features. I can't talk about all 140 of those unless you just want to read eye charts for the rest of my talk, which wouldn't be very exciting. So I picked a few that I wanted to highlight and share with you on work the community's been doing. So I'll talk a little bit about procedural SQL, about LLAP, HBase, work to make so you can store the metastore in HBase, some of the improvements in the Hive on Spark areas, work we've done in the cost-based optimizer, and then touch really, really quickly on some of the other features. So let's start on procedural SQL. So as I'm guessing most of you know, there are different database vendors have different things that they use to make SQL procedural, right? SQL, as initially specified, is not a Turing-complete language. It's query language. You can say select this, whatever, but you can't loop, you can't branch. So basically, you can't write procedures in it. Oracle has PL SQL, Teradata has stored procedure language. All these different databases have extensions to SQL to deal with that, so that you can write an actual workflow in it. You can write a stored procedure, those sorts of things. So in Hive 2.0, we have a first version of that. It's called HPL SQL. This was a contribution from the community. It was added by a new committer. The goal of this is to be as compatible as possible with the dialects out there, like Oracle's PL SQL, so that the port from those is as easy as possible. Currently, this sits outside of Hive. It's not inside Hive itself, so you run this module external to Hive. It communicates with Hive via JDBC, and then submits your queries after it's executed the loops or branches or that kind of stuff. Our goal is to integrate this tightly so that you could actually submit your entire PL SQL directly to Hive via command line or script or JDBC, as you do with standard SQL today, and that would all just work. But that is there in 2.0. You can use it, play around with it, and give us feedback. Okay, so the next thing I want to touch on a little bit is LLAP, which at least initially stood for live long and process. I heard it, somebody in our team tried to rename it the other day, long-lived analytic processing. I'm like, okay, what are you're trying to like unnerdify the name here or something. But anyway, it was originally named live long and process. The idea here is that, as I said before, Hive, as with all Hadoop things, was originally batch, which means that when you submit a job, you have to spin up containers, tasks to run that job, right? In the world that Hive and Hadoop came from, where jobs were going to run from minutes to hours, often hours, sometimes even days, that was completely fine. If it took you 30 to 60 seconds to allocate containers and spin those JVMs up, no problem. Who cares? Your job's going to run for 2 hours anyway. It's absolutely silly to spend time trying to optimize away that 30-second startup time. As Hive has migrated from running just these big batch jobs to also running jobs where there's a human sitting at a terminal typing queries or maybe clicking on on some kind of reporting tool, obviously that 30 seconds is no longer acceptable, right? Try to envision if Google took 30 seconds to start returning you search results, you'd quickly be finding alternative search engines, right? So with the work we've done up till 2.0 with Tez and Spark and some of these new engines, we can drive that time down quite a ways from where it was. It doesn't have to be in the 30-second range anymore. It can be in the 5 to 10-second range for that startup, maybe even down to 2 if you push really hard. But it's hard to get that last couple seconds out when you still have to do container allocation. And so LLAP provides a set of persistent daemons so that are standing running processes on the data nodes that can start to answer queries immediately. Once you have these running processes, there's a number of other benefits. One of the big ones is your code has already been run through the JIT, right? We find that the performance speed up after the first, say, 10,000 records, once the code gets run through the JIT, is actually pretty tremendous. And so not having every user have to go through that when they start up their processing actually turns out to be a big win. Also, another obvious and huge example is that we can start to cache data. And we can share that cache. So if you and I happen to be reading the same data, which does often happen, right? Because as your data comes in, it's often the most recent data that everybody wants access to. That's the hot data. And so if we can cache that data and share those caches effectively, that is a huge win for being able to both efficiently use memory in your cluster and answer queries quickly. LLAP, though, is more than just a cache. It can also execute operators inside that cache when it makes sense. So if you go to read data and it's cached in LLAP, LLAP won't just stream you all the records back from the partition or whatever that you are reading. It is aware of things like columns inside the columns that you need, so it can just send you back the columns that your query requires. It can apply filters. It can even apply aggregates and joins and that sort of thing. Now, I want to be clear here that not everything makes sense to run through LLAP. This is very focused toward a certain type of query, which tend to be analytic queries where you're going to do some kind of star join, aggregate it, maybe sort it, and produce a small output set. That's kind of the classic use case for this. If you're going to do a large ETL style query, or maybe say a fact-to-fact join, or something where you're going to be touching tons of data, one, the caches aren't going to tend to work well for you. And two, that's exactly the use case where Hadoop, more traditional Hadoop, shines. So we are not by any means saying that all queries will run in LLAP always. It's not always the right answer. Right? Sometimes it is, and sometimes it isn't. The other thing that doesn't make sense to run in LLAP, or actually that we don't want to run in LLAP, is user code, because then we have a security problem. If both my code and yours is running in, or if both my query and yours is running in LLAP, and I put in a UDF, I could be somehow jumping inside the process space and sniffing at your data when maybe I don't have the security permissions to do that, right? So we don't allow user code to run inside the daemons either. And then additionally, we want to open this up so that other people besides Hive can make use of this. Right? Hive's certainly not the only engine that's interested in being able to read data in parallel out of tables and apply various transforms on that data. So we're working on an interface to allow other engines, and Spark SQL is the first one we're actually working on, where it would be able to submit a query, some portion of the query it wants to run on, or a table it wants to pull data from, to Hive and get back a series of parallel pipes from LLAP to be able to read that data very efficiently and quickly, and then go on to do whatever work it wants to do on that data. LLAP is available in 2.0. It's, as I've said, beta. And there's Gopal is doing a talk on this tomorrow, I think, where he will actually do demos of the system, show you some queries, show you kind of how it works and the speed. So if you're interested in this, I strongly encourage you to go to that talk. So just a little bit more detail on how exactly this works. On the left here, you see the way Hive works in a TES-only situation, right? Where all the tasks run as separate containers in TES. They're submitted as one job, as a graph, that TES can then efficiently execute, but those are all separate containers. In the mixed mode here, you see a case where we start to read out of LLAP, those green and white boxes toward the top with the orange bars in them are supposed to be LLAP daemons. So you do some of the processing there, and then maybe you have a big join or something that you're afraid would blow your memory out, so you don't do that inside the daemon. You're still going to farm that out to additional containers in the node. And finally, if you have a query that you estimate can fit entirely inside the daemons, you can run them that way. And then in that sense, in that case, you would never actually have any extra containers out in the, that you'd allocate out from TES. So you can run in any of those three modes. Ideally, what you would like is our Hive's cost-based optimizer to figure out which of those you should use for a given query. Unfortunately, that's not the case at the moment. Today, you as a user have to make a decision on what you want to do there. Obviously, that's not our end state, that's just where we're at today. We need the optimizer to be making that choice for us. So let me just whet your appetite here a little bit with numbers. So this is a comparison of Hive 1.x versus LLAP on the TPCDS query set at 10 terabyte scale. So that means the entire data set is 10 terabytes. This is run on 20 machines, I think with 256 gigs each of memory. So you can't, you're not going to fit all that in memory. We didn't cheat and just preload the entire set into memory and then go, hey, look, we're really fast. But this gives you an idea of some of the queries. Now, these are the best case ones. Here, I'll show you actually the whole set. This one's a little harder to read, but you can see that LLAP doesn't actually win in every case, right? There's cases where it's actually slower. Part of that is, as I said, it's new code, it's beta. There's places it's not necessarily making the right choices. And then, as I said, there are certain types of queries that LLAP is not the right choice. You wouldn't actually want to use it. So as an amusing anecdote, I asked, these numbers are actually a few months old, and so I asked Gopal this morning, I'm like, are there different, do you have newer numbers that I should be using? Do I need to change my slide? And he said, no, we don't have new numbers, but it actually installs now. So you can see where they've been spending their time hardening this and making it much more usable and good to, ready to be up and going. Okay, so limitations. Right now it's read-only. There isn't a write path through this yet. So if you, when you write code, that still goes through the old path, which is fine. I mean, LLAP will figure that out. You don't have to refresh the cache or anything. But that means that we haven't necessarily sped up the right side of the pipeline. Also, the new ACID functionality does not yet work with this. If you're querying from an ACID table, you'll just need to not use the LLAP route. So you can, to be clear, you can use ACID and LLAP in the same cluster. You just have to, for those tables, you have to not use LLAP to query them. And again, that part of that is we have to get that right pipeline working. As I mentioned, you, the user, have to decide when to use this, which is not what we want. Today, this works with ORC files, and that particular piece may actually continue into the future because there's a lot of heavy integration with caching file footers out of ORC in order to efficiently determine which parts of the files to cache and which parts to how to do split calculations and all that kind of stuff. What I would like to see here is that we're very efficient about picking up, if you have your data in another format, it might look to you like it reads it, even if what we're actually doing underneath is quickly transforming it so that we can into ORC so that we can handle that data. But that may be a much better solution than us trying to make this work well with every existing file format out there, right? And then currently this actually depends on some pieces in TES to make it work. So you have to use TES as an engine because it actually uses the TES AM to drive some of its parts. Okay. So actually, let me back up a couple slides here and show you something that is interesting. So let's look here at query 55, which is the fastest query. You see that's in this LLAP, the green bar there. We're taking 2 to 3 seconds to execute that query. I'm working from memory here, so I might not have the numbers exactly right. But when I went and looked at where are we actually spending a time there, half a second is spent actually executing that in LLAP. 2, or maybe it was 1.5, of those seconds is spent planning the query. So we're actually in this weird spot where for some of these queries we can execute them faster than we can plan them. Now the TPCDS query set schema is pretty heavily partitioned. So this query is accessing somewhere around 1,800 partitions. The way Hive's Metastore is laid out, that means it's having to gather that data for those 1,800 partitions and the stats for those 1,800 partitions and pull it all in. So obviously we need to figure out how to speed that up. We need to be able to handle metadata faster. So how are we going to do that? Our proposal for how to fix that is to look at using HBase as our metastore instead of a relational database. So as maybe you know, today Hive actually stores all its metadata in just a standard relational database, MySQL, Postgres, Oracle, whatever you want. Now, the way you traditionally do that, right? You have a bunch of Java objects, you want to store them in a database, you use an ORM layer. It makes coding very simple, makes, some other layer handles all that translation for you. But the downside is you come out with these, well, there's a couple downsides. One downside is you come out with a horribly complicated schema. Hive tracks something like 7 or 8 different types of objects: databases, tables, partitions, user privileges, views. There's a couple more I'm sure I'm forgetting. But you end up with 40 plus tables in the metastore to track this. So your metastore is, your schema of your relational database, it turns out to be very complex. And because it's denormalizing everything, you actually have to do either very complex joins or many queries to get each thing. So for each partition in the Hive Metastore, every partition in your query, Hive has to do, I believe it's 8 separate queries to fetch all that information for that partition. And then it has to do another 4 or 5 to fetch the stats for that partition. So now all of a sudden you start to see why when you have a query that has 1,800 partitions, it takes a couple seconds to do the planning. You're spending most of that time just fetching data from the Metastore. That's not a good model. The other problem that the ORM layer gives us, this is both a feature and a problem, is it makes it easy to use lots of different databases. This is very good because every user has a different favorite database, right? Some people like Oracle, some people like MySQL. Usually your company or group or whatever will have some database to use for everything and you want to use that. That part's a feature. But the part that's hard is that means you can't optimize against any one database. If we could pick one database and hand tune our SQL, we could make it a lot faster. But if we start trying to do that for the 5 databases that Hive supports today, that's a lot of work and debugging, and it's just a lot more effort for the Hive community, right? And frankly, it's hard to keep right because not everybody has every instance of every database, and so you tweak one thing and you end up breaking somebody else's database implementation and you don't even realize it because you can't test against that. Having a relational database also limits our ability to cache things because you can only fit so much data in there. And people always come up and say, hey, but relational databases can store lots and lots of data. That is true, they can. If you buy very expensive databases from some vendors, you can store terabytes of data, no problem. But we have to run on out-of-the-box MySQL. We can't have, yeah, we're a great open source product, only you have to go buy this multi-million-dollar proprietary database to make us actually go. That's not that's not reasonable. So we have to limit how much data we actually store in there. Now we can easily fit all our actual data catalog data, but we would like to aggressively cache things. We'd like to cache stats for the columns very aggressively. We would like to cache file footers so that we know what portions of files to read. And we already have the indexes that are in those ORC file footers in the data catalog. We just can't do that with a kind of vanilla relational database. You also have to limit the number of concurrent connections you have. These databases aren't built for hundreds or thousands of things to be talking about to them at the same time. That means we have to do all the planning up front. We can't ever delay it until partway through the query. Right? All these things are something that using HBase gets around for us. HBase is already built for big data. It handles lots of connections. You can stash lots of stuff in it. You can just store your objects as objects. You just serialize them in a protocol buffer or whatever. Boom, good, you're ready to go. So our goal is to cut that access time for querying thousands of partitions from around 2 seconds to around 200 milliseconds. We're not all the way there yet. We made it about halfway. Right? We've cut it about in half. We'd like to cut it by another factor of 5, but we're at least started on it. Now, I don't want to paint this as a super, all rosy picture. There are challenges involved in using HBase, the biggest one being that HBase itself doesn't provide transactions. And we need transactions. We don't want to be in a situation where you say drop table, and it gets halfway through dropping the table's partitions and blows up, and so now you have a table that only half your partitions are there, but half are gone. That won't work, right? We need real transactions here. So we're working around that by using Apache OMID, which is a open source transaction handler on top of HBase, developed at Yahoo, to put that in there so that we can have the transactions we need. This is also in Hive 2.0. It is definitely alpha. It's there, you can play with it, but it's not 100% ready to go. The basic functionality is there. What's really missing is all the integration, like how do I install this nicely? How do I monitor what's happening inside of it? How do I back it up? How do I replicate this data somewhere else? All those questions haven't been dealt with, and those are the things that we need to do to really drive this to completion. Okay, I talked too long about that. I need to speed up. Okay, so Hive on Spark. As you guys probably know, with the addition of in Hadoop 2.0 is we can have various engines besides MapReduce in the back end. Hive has Tez, but it also has Spark as an engine that can execute stuff. A lot of work has gone into that in Hive 2.0. This includes dynamic partition pruning, so now the Hive on Spark is much better at figuring out which partitions it needs to read. Instead of taking every partition that might be in a query, it runs a job first to do some filtering and figure out, okay, I only need these particular partitions. And I'm not just talking about a where clause here where it's easy, where you can see it beforehand, but things like joins where as a result of the join, you may actually be able to prune quite a few of the partitions. That's the kind of thing that this can do and do much more efficiently. It now makes much better use of Spark's persistence for situations where the same relation ends up happening multiple times in the query. So say you're doing a self-join, rather than actually accessing that data twice, it persists that table or the portion of the table you're going to self-join into an RDD in Spark and then can reuse that for each side of the query, thus being much more efficient. There's been work to do to improve vectorized map join and other parts of the map join so that that is much more efficient in Spark than it was. And then also work to make use of the parallel order by that's already available in Spark. So traditionally in Hive, order bys are always done in a single task, which is usually okay, because usually you're not ordering until you get to the point where you've done all your query and you're going to present results to the user, and you're probably going to present not that many rows, so that's fine. But occasionally you actually do have something large that you want to sort, and so now this can make use of the underlying parallel order by in Spark to do that. Pre-warming containers, that is, when you start up Spark and you start running your job, you may not have all your containers online yet. And if you start your job as soon as you have some containers, Spark will actually figure your parallelization by the number of containers you have available. And so as those additional containers come online, you'll actually not be using them because the parallelization calculations are already done, and they won't take those new containers into consideration. They resolved some of those issues. They added support for Spark 1.5 and then lots and lots of bug fixes. Okay, and then cost-based optimizer. So Hive traditionally had a rule-based optimizer. In starting several releases ago, we started using Apache Calcite to do a cost-based optimizer. This allows you to optimize things like join ordering, where there is no rule that can tell you a priori what the right answer is, where you have to actually look at the statistics of the data and make some estimates about how much it's going to cost depending on the plan you choose. In 2.0, we have continued to do a lot of work in the CBO, and we've gotten it to the point where we believe it is almost always giving better query plans than with it off. And so we turn that on by default now. In the 1. line, we were still, it was still pretty new. Sometimes it gave better answers, sometimes not. So we've gotten it hardened to the point where where it's giving good answers most of the time now. A lot of this focus has been toward BI queries using like the TPCDS query set. So that's where we've really focused. And a lot of it also has been focused on better stats collection, because the optimizer is only as good as the stats you put into it, right? So we've gotten much better at our stats estimation. As I said, in addition to that, there are many, many more things that have been added. And a version of these slides is actually already on SlideShare. I'll post this version, but none of this has changed, so you can go look through this and see some of the new stuff that's there. Let me talk just a little bit about incompatibilities. What did we break? Not too much, actually. So we did get rid of Java 6 because it was end of life a long time ago. A big one is we got rid of Hadoop 1. So this will no longer run on Hadoop 1. It does require Hadoop 2. I don't think that's a hardship for anybody, but it makes our programming much easier, enables us to remove a number of shim layers in Hive itself. We deprecated MapReduce as an engine and now recommend that you use either Tez or Spark, because we believe those have matured to the point that they're what you should be using. We haven't actually removed MapReduce yet, partly because we know this is a big change and we want to give people time to prepare for it, and also because honestly some of our test code still depends on it and we couldn't remove it right now if we wanted to. But that's where we want to be headed toward. We made some default configuration, some of the defaults for configurations have changed, where we're starting to just change configurations to be what we think makes sense for the most people. We're also actually actively trying to reduce the number of configurations. We have literally thousands of configuration options. That's just out of control. So we're trying to pare that down so that in cases where no one's ever using these config variables or where they don't even make sense anymore, we're starting to remove those. And then the other big one is we do plan at some point in the future to remove the Hive command line as a command line tool that sits on a gateway where you need direct access to HDFS to run your queries. Now that doesn't mean there won't be command line access to Hive. Beeline will be that through Hive Server 2. But the reason for that is you just can't secure the system when somebody's sitting on a gateway machine and has full access to the file system to run their jobs, which is what you need if you're working with the command line. That that just opens up security holes that can't be plugged. So that's the direction we're going. Again, we're not there yet. This is just kind of a notice that that's the direction we want to move. Okay, and with that, questions? And the lady with the mic will run and right here.
How does this compare to your recent partnership with Apache Hawk or Pivotal Edge DB?
Okay, so how does this compare with Hawk? So Hawk is another SQL engine out there on Hadoop. I kind of, from the Hive community perspective, we're kind of moving toward the same direction. We want to be a data warehousing solution. I'll let the Hawk people talk about what's good about Hawk, but from a Hortonworks perspective, this gives you choice on what you want to use, right? I think probably what's good about Hawk there is it's ANSI SQL compliant today. It's fairly fast for certain data sets. I don't think it scales quite the way that Hive scales.
I'd go ahead and segue on with the same question with regard to Apache Drill.
Okay, so I'm not super wild about answering for other projects because I don't want to be speaking for them. But I think Drill's strength is more in they can run on lots of different data sets, right? So my feel anyway is they're a little more focused on we can run SQL on anything, whereas Hive's focus, when you see what we're spending time on it's things like better query performance, complete SQL, complete 2011 SQL, ACID. We're trying to move more toward data warehousing. But you really should ask the Drill guys that question too, because I don't want to be putting words in their mouth. I think there was a question over here. This mic running doesn't work.
With regard to the user-defined code, you mentioned that you did not allow that to be in the shared container. Do you mean UDFs that are written or some other definition?
Yeah, user UDFs. So what we do want to allow, so Hive has its own UDFs, like count and sum are implemented as UDFs, right? So those obviously will run in there. We want to give an ability also for admins to bless a UDF, because you might have something that you've written, maybe you have a sessionization UDF that you run in your company and it's safe, you've examined it, all that. So we want to enable that. What we don't want is just, hey, I'm the new guy and I show up with a UDF and you don't know what's in there. And probably I'm not malicious, but maybe I don't know what I'm doing and I blow the thing up or something.
That's our case exactly. We have blessed UDFs that we need to operate. We just need to be able to assign those as trusted.
Yes.
Thanks.
Okay, and I think sorry. Okay.
I have one question. I want to ask about the query parsing concurrency. Is it handled in this one?
Yeah, it is. So the lock where you can only parse one thing at a time has been removed.
Okay.
So you can do that. I think this gentleman over here in the corner has been waiting patiently for the mic.
Any plans for the time period operation from SQL 2011?
Okay, so any plans for the time period operation? So are you meaning like interval or what?
The interval overlap so that you can, when you have...
Yeah, so we do want to get there. I can't give you a time frame, but we're wanting to get there. And actually some interval stuff, like we actually do support interval underneath in some ways now, we just don't expose it out. But I can't give you by next year we'll be there. But yes, basically our goal is everything in SQL 2011 that we believe is applicable to data warehousing, we want Hive to be able to do. Right? All right, my clock is running out. So thank you all very much.